Hi, I worked with Dr. Goswami. He spoke last week, so the majority of his work is to find personalized medicine to help breast cancer patients. I'm doing genotyping mice. So I didn't do So for now, I was just observing the other his undergraduate. Yeah, and I worked with Yeshiva University. What is genotyping? So essentially, genotyping is to examine the individual's DNA sequences, like the A, G, C, T, the nucleotide order. And genotyping is used it can be used in research to find ways for personalized medicine, and in my case, for breast cancer. So the goal for the genotyping was to identify the mice with the PYMT gene, and this gene, it induces tumors. So in his lab, there's either you're injected with this gene, or the gene that stops tumors is taken away. So in my case, the gene was inserted. So the brown mice was the wild type, and it bred with the white mice. So the wild type. And so the brown mice were mainly wild types, and the white mice had the PYMT gene, and the pups were used, and at 3 weeks, the pups are separated from the mother, and will be used for the genotyping process. So I separated the methodology in 3 parts. So preparing the DNA, the PCR process, and electrophoresis. So my materials. This is what I used to prepare the DNA before PCR. So the oxygen tank was used to put the mice to sleep, and the mice will only sleep for 20 seconds. So you have to cut the tails quick for the genotyping. And then the second one is PCR, and these are materials for gelic electrophoresis. So the first step was to put the animals to sleep with the oxygen tank, and the tails will be cut quickly since they get up within 20 seconds. And if they do get up, they get really angry and they'll try to bite you. So the tails will be placed in the genomic DNA buffer, and it depends how many samples. So if there was 5 mice, there will be 5 samples. So the samples would be frozen overnight, and when you see the samples the next day, you will see that the tail looks white. And then the samples would be centrifuged, and at these conditions, 14,000 RPM, for 5 minutes at room temperature, and by that time, the centrifuge, the DNA pellets will be revealed. And then mainly you only want the supernatant, which surrounds the tail. You don't want the tail for genotyping. And then you take this 100 microliters of the supernatant and place it in different tubes. And then you add 10 microliters of this and 300 microliters of ethanol, 100%. And then the tails are not needed, so they're stored in a freezer. I don't know what they do with the tails. So the supernatant mixture will be in the freezer for 30 minutes. And then it will be centrifuged at 14,000 RPM for 10 minutes. And the DNA pellet is revealed. and then you discard the supernatant. If there's a little bit supernatant left, it's okay. And then you add 100 microliters of 7% ethanol, and you centrifuge again. And after you centrifuge, the DNA pellet, you won't see it as clear. So when you discard the supernatant in this process, you have to be careful, since you might remove the DNA by accident. And in this process, you have to take most of the supernatant out. And then, since it's ethanol, it evaporates quickly, so you can air dry for 10 minutes. And then you add 50 microliters of nucleus-free water, and this is used for the nanodrop. And then briefly pulse to mix. And then add 1 microliter the sample to the of each sample to the nanodrop and measure. So the nanodrop measures how much the DNA weighs. It should be between 8 and 15 nanograms. If it's anything more or less, then you have to add distilled water. So the next process is PCR. So the PCR, add to the PCR tubes genomic DNA, PYMT primer magnesium Amomix, nucleus-free water. And the reason this is X and Y is because when you do the PCR, one tube will act as the control. So in the control, there will be no genomic DNA, but to make up, it has to be, wait. So to make up for the DNA, you have to add 1 more microliter of nucleus-free water. So normally it'll be 2 microliters, but in the control it'll be 3 microliters. Place in PCR machine, and these are the conditions you have to set. So the denaturization, annealing, and extension. This is a cycle. It will be repeated 45 times. And then this is the loading die, which dyes the DNA for electrophoresis. So this is the process to cast the gel. So you add agarose and 50 milliliters of TAE in a flask, and you briefly mix and heat in a microwave, and you have to. When you heat it in the microwave, the agarose should not be visible anymore. If there's still white powder, still agarose, then you have to keep it in the microwave for a few more seconds. And then you add ethylene bromide, and this keeps the gel from breaking. Because if you don't add this, the gel will break when you lift it. You swirl the mixture and pour in the casting tray with a comb, and the comb will create lanes to put the samples, and then the gel will harden for about 30 to 45 minutes, and then the gel will be placed in electrophoresis tray and cover with the TAE. The hyperladder helps the samples to spread across the gel, and that'll be placed in the first lane, and then 10 microliters of the PCR products will be placed in the remaining lane, including the control. And then perform electrophoresis for 30 minutes at 100 volts. And then you image the gel in the gel documentation system. And then the conclusion is how these samples will be used for further research, since I'm still new and they didn't really explain this much. And then the mice that will be positive will be used for breeding, so they'll be breeding with more wild types, unless they die. Also, if the control, when you do the imaging for the electrophoresis and the control ends up being positive, that means the sample is contaminated, since it might be because of the process before, while preparing the DNA, that some of the chemicals were old and they contaminated. These are the references I used.